Welcome back for day 2 of the International Science School online edition. Today we are kicking off with a lecture which I'm personally really looking forward to, because it's hard to find a more fascinating topic for a Tuesday morning than basically the entire universe. Our speaker this morning has one of those jobs where I would love to be a fly on the wall when he goes to a party and someone says, "What is it that you do?" And he says, "Well, actually, I'm a professor of astrophysics at the University of Sydney, and I study basically dark energy and dark matter in the universe and how that all comes together to define how we exist at all in the universe." Our speaker was born in Wales. He's a proud Welshman. Studied in London and Cambridge before coming to Australia in 2000 and then joining the University of Sydney in 2002, where he's been making trouble ever since. Would you please make very, very welcome for a Tuesday morning lecture, Professor Geraint Lewis.
Thank you and good morning, everybody, and thanks for coming along to listen to me this morning. As Chris mentioned, my name is Geraint Lewis, and I'm going to talk to you about an area of my research which basically causes a lot of controversy. So what I want to talk about today is this notion of fine-tuning in physics and what its implications are and where I feel the field is actually going. Now, just to give you a very brief introduction, so I'm a professor of astrophysics here at the University of Sydney. I'm part of the Sydney Institute for Astronomy, and I do a lot of research around the dark side of the universe. So I'm very interested in understanding dark matter and dark energy, the stuff that it basically shapes the universe around us. To do that, I do both theoretical work, I do theoretical cosmology, I generate synthetic universes, but I also do observational work, whereby I try to measure the amount of dark matter and dark energy out there. And I use fields such as gravitational lensing, where light gets distorted as it travels through the universe, and galactic cannibalism, where one galaxy consumes another, to try and reveal where all this hidden stuff is. A lot of my research these days is very computational. I'm trying to push ahead with using artificial intelligence and machine learning in astronomy. We've just got so much data, analyzing it is becoming rather problematic. But what I want to do today is talk about an area which I've been working on for a number of years. As I mentioned, it can be kind of controversial. And a few years ago, I wrote a book on this very topic called A Fortunate Universe, Life in a Finely Tuned Cosmos. And what I'm going to do today is describe this notion of fine-tuning, what it means and what it could imply for us. Now, this is at somewhat the edge of what some people would call mainstream science. Some people say it strays into pseudoscience. It's definitely an area that the philosophers really enjoy. But we'll go through the key concepts and we'll talk about what fine-tuning means and what it implies. So let's start off with something I think we can all agree on. We agree that we live in a beautiful universe, right? One of the reasons I am an astronomer is because the night sky is very, very beautiful. And I remember the first time I went to a large telescope, went outside, I saw the dark night sky, stars from horizon to horizon, and realized just what a beautiful universe we live in. Of course, with telescopes, we can peer deeply into the universe and we see lots of beauty, right? So we can see clouds of gas, groups of stars. We know that stars have lives, they're born, they live, and they die. We see stars that live together in galaxies. Now, me as a cosmologist and an astrophysicist, I appreciate the beauty, but what I also want to know is, where does this beauty come from? What we know, of course, is that the universe must be shaped by the laws of physics around us. It's the laws of physics that make stars shine, make gas clouds collapse, and make galaxies rotate. So what I want to do as a cosmologist is apply the laws of physics to the universe to understand how the universe overall behaves. Now, of course, there's a lot of beauty in physics, and beauty's in the eye of the beholder. And some of us find mathematics kind of beautiful, others find it kind of daunting. But one of the things I think which is most astounding is that one of the greatest successes of the last century has been to simplify physics to a huge degree. Now, I don't mean simplify physics in terms of the mathematics, right? We all know that even the mathematics of describing the simplest objects you can think of, we talk about particles and atoms, etc., that can be kind of complex. But as I stand here in this empty lecture theater, I wish there were people here with me, I look around and I see all kinds of different stuff. I see air, I see the wall, I see stone on the floor, etc. Over the last 100 years, of course, what we've been able to do is that we've taken all this messy stuff around us and we've been able to sort it out into simpler and simpler pieces. What I mean by that, of course, is that what we've come to realize is that everything is made of atoms, okay? So I myself am made of collections of atoms in molecules, but then again, so is the air, so is the stone, so is the wood of the desk, etc. We originally realized, of course, that there were 92 individual elements or natural elements in the universe, but we went further. What we wanted to do was ask the question is, we know that these elements are the same. Each bit of hydrogen is like another piece of hydrogen, but what's that hydrogen made of? We know that those are made of individual atoms, but we've been able to slice atoms up into simpler pieces. We know that all of the atoms are just made of 3 basic building blocks. In the nucleus, we have protons and neutrons, and orbiting the nucleus, we have electrons. And so I'm made of many different kinds of atoms, but the only thing that's different about them is the number of protons and neutrons and electrons involved. Of course, we've been able to strip the universe even further, right? What we've realized, as well as the protons and the neutrons and the electrons, that there is essentially a set of Lego blocks in the universe, the fundamental particles, as we call them, right? So we have the electron, but we realize that the proton and the neutron themselves are made of smaller things. But as well as those particles, there are other particles out there, and we've been able to chart those other particles to a very high degree. As well as the particles that make up stuff, we've also discovered how particles talk to particles. And what I mean here are the fundamental forces. We now know that there are 4 fundamental forces in the universe: gravity, electromagnetism, the strong force, and the weak force. And we've been developing a language to describe those forces. And they are the glue that basically holds stuff together. And right at the very bottom, one of the great successes, of course, is that we've realized is that the stage on which all of these particles and forces play out their lives, the notion of space and time themselves, are a fundamental thing which is not rigid, but is malleable. Einstein showed us that space and time can sort of bend and stretch, and that gives us aspects of gravity. So we've really stripped the universe down from what seems like a myriad of complexity into some basic building blocks, okay? Building blocks, glue, and the stage on which they play. So for a physicist, that's great, right? What we've done is we've simplified the universe. So if you talk to a particle physicist, what is the universe made of? This is what they'd say, right? The universe is made of fundamental bits, and they come in groups. So one group, that's the quarks. Now, there are 6 quarks. Why there are 6, we don't know. They appear to be arranged in pairs. So there's 3 sets of these pairs. Why 3? We don't know. But we've been able to chart their properties. And we've got the lightest 2 quarks, which we call up and down. We have sort of middleweight quarks, which we call charm and strange. And we have heavyweight quarks, which we call top and bottom, or truth and beauty. Of course, these names are just labels. They don't actually mean anything in particular. So they are basically the mass of stuff in the universe. Now, accompanying these quarks, we have another similar family, which we call the leptons. Now, in the leptons, the E you can see there, that's the electron. So we know that electrons are very light, but they are the things that are essential to make up the atoms around us. Now, the lepton has some cousins. It has a heavier version of itself called the muon, and a very heavy version of itself called the tauon. Again, there are pairs of these particles, so it's not just the electron itself, but it has a companion, which is known as the electron neutrino. The muon has a companion known as the muon neutrino, and the tauon has a companion known as the tauon neutrino. Again, why there are 3 pairs of these things, we don't know. We think that's telling us something deep about the universe, but we haven't worked that out yet. Now, for us, around us, everything we see, as I mentioned, right, we're made of protons and neutrons and electrons. So these are the fundamental building blocks, and the only ones we really care about are the up and down quark and the electron. Why the up and down quark? Well, if you add 2 up quarks and a down quark together, they make a proton. And if you add 2 down quarks and an up quark together, they make a neutron. So you can split every proton and neutron apart. You'd find inside that they are made of up and down quarks. So that's it. That's what the universe is made of. But of course, what I said is that we also need that glue. So we need the fundamental forces. And so there's a separate group of particles, which we call the bosons, are the ones which manage the forces. So there are 5 of them in this particular picture. The one at the top, which is a capital G, it's in a little bit of a dashed circle. That's the graviton. That is a hypothetical particle that we think is responsible for the force of gravity. Now, there's been a big problem with us trying to make gravity work with quantum mechanics. That's another lecture altogether, but it's a hypothetical particle that people are hunting for. But the others, we know and understand quite well. Firstly, at the top, we've got the W and the Z particles. They're responsible for the weak force, the weak nuclear force, which is responsible for aspects of radioactivity. Then we have 2 particles. The G there is the gluon. That's the one that holds the quarks together to make the protons and neutrons, and holds the protons and neutrons together to make atomic nuclei. And then we have the photon, which is responsible for the electromagnetic force. And of course, there's one more boson that we have to add, probably the most famous boson of all. That's the Higgs boson. And that was, of course, only discovered in the last decade. And we know that the Higgs boson and the Higgs field are the things that give fundamental particles their mass. And this is it. This is all we need. Now, I'm not saying that all of physics is solved, but we've been able to strip down the universe around us as we see it into these basic pieces. How do the forces work, though, right? I'm sure you've done your Newton's gravitation, you've done Coulomb's law, you've spoken about forces acting over distances. Why have we now got these particles to account for forces? Well, it turns out that when you talk about quantum mechanics and forces, the way forces act are very different to what you have in your classical physics picture. So here we've got a little schematic. We've got 2 electrons, and we're just going to get them to interact. Now remember, in classical physics, according to Coulomb's law, there's a force between these electrons. So if they fly towards each other, that force increases, they would repel, and they'll move apart again. This is what happens when we take a quantum mechanical viewpoint. The electrons trundle towards each other in a straight line. They exchange a photon, and their paths are deflected. So forces in quantum mechanics are due to an exchange of particles, and the particular particle that is exchanged tells you which force is involved. So if I was going to do a strong force, there would be a gluon exchange. If it was a weak force, it would be a W or a Z particle that's exchanged. Now, this picture might look familiar to some of you, right? This is what's known as a Feynman diagram, named after Richard Feynman, who won the Nobel Prize for his work on quantum field theory. He did his work in the 1940s, won his Nobel Prize in 1965. And these Feynman diagrams have become so iconic in physics, right, that you find them everywhere. So the picture of the van there, that's Feynman's van. He actually had Feynman diagrams painted on there. And all you've got the various lines and squiggles. Those are precisely what we've been talking about. Particles are talking to other particles by exchanging other particles again. And the picture up there is Richard Feynman with a stamp and a whole collection of Feynman diagrams on there. And it works. This is the terrifying thing, right? Physics works at a very high degree. If I want to describe an experiment using quantum field theory, and I can use Feynman diagrams to calculate the strengths of the forces, I do my experiments to measure properties to something like 12 decimal places. It works exceedingly well. So this description of the universe is very, very good. Okay? It's the best description of the universe we have. But there are some issues. Okay? Let's think about the issues that bother people. Now, it doesn't bother all physicists. Many physicists are like, oh, I'll just get on with my day job. But for a number of physicists and philosophers, let's talk about the things that bother them. Now, let's take an example that you might be quite familiar with. Here, I've got two bodies, okay? So these are massive objects. We're going to put them in space. And of course, because they're massive objects, there is a gravitational force between them. And we'll only worry about Newtonian force right now. We won't worry about Einstein and relativity. But we can talk about the force purely in terms of Newton's laws. So we know that if I've got these two particles, and they've got two masses, M1 and M2, it might be the Earth and the Moon, or the Sun and Jupiter, or whatever, I can calculate the force between them. And you've seen the expression to calculate that force. The force is equal to minus G, Newton's gravitational constant, times the mass of one times the mass of the other, divided by the distance between them squared. That gives you the force. Brilliant. And it works really well, of course. If I want to send a space probe to Pluto, and I've got to send it through the solar system, it's going to be tugged on by all the planets as it travels. But if I want to work out that particular motion of that space probe, I just need to use Newton's laws. Again, it works really, really well. But there's a question. Where does G come from? Right? We know it's a constant that goes into this expression, but where does it come from? Now, you may have done some experiments yourself to work out G, right? You may have done a famous experiment as done by Cavendish, where you take some masses and you measure the force between them. But the realization is that you have to measure G from nature, okay? So if I want to use Newton's laws to calculate the motion of an object through the solar system, or even a star around a galaxy, then I need to measure G in the laboratory first before I can use that theory. And that's a little bit of a head scratcher, because you might think, oh, physics is very mathematical. Surely I do my mathematics and I end up with my mathematical expression and that's all I need. But you don't. You need to ask nature for information before you can get your mathematics to work. Now, of course, it's not just G, right? Now, in our, when we do our experiments, we know that G has this particular value in these particular units, right? 6.67 times 10 to the minus 11. But think of all the other constants of nature that you use when you do physics. Numbers which you get by interrogating nature, okay? Speed of light, 2.99 times 10 to the 8 meters per second. The mass of the electron, it's really tiny, but it's a specific value, 9.11 times 10 to the minus 31 kilograms. Then there are other numbers, right? The charge on the electron. Now, I'm sure when you've done electricity and magnetism, the teacher's just gone, and the charge on the electron is, and off you go. But where did that number come from? That number had to be measured, right? It didn't appear out of the mathematics. It had to be measured and put into the mathematics. Planck's constant, the number that tells you about quantum mechanics, has to be measured. And then there are numbers that tell us the strengths of the fundamental forces. Alpha, this is a number that tells you the strength of the electromagnetic force, has a value of almost 1 over 137. And then there's an equivalent one for the weak force, which is 1 over a much larger number because the force is weaker. Where do these numbers come from? You have to ask nature. Now, if you're a practical physicist, you might just say to yourself, well, okay, my job is to do an experiment or make a prediction, etc. I'll measure this value, I'll make my prediction, I just move on. But for some physicists, these numbers are worrisome, right? And I'm going to put a quote up here. It's a quote by Richard Feynman, okay? He's talking here about alpha, the fine structure constant. All good theoretical physicists put this number up on their wall and worry about it. Immediately, you would like to know where this number comes from. Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding. So we have a whole swathe of these constants in physics that we use, that we have to measure from nature. And Feynman was asking, why is alpha 1 over 137? Why isn't it 1 over 13 or 1 over 13,000 or 1? So you could ask yourself the question of, if alpha was different, what would the universe be like? What we're going to be doing is we're going to be playing a game which real historians hate, okay? There's a branch of history called alternative history, or what-if history, right? Now, to a historian, history is what happened. And if you want to change what happened, then it becomes fiction. It doesn't become history anymore. But there are plenty of people who write proper fiction books, right? Whereby you take a story and you change something historical which happened, and you try to explore the consequences in a fictional kind of way. And there's some examples here. You might have heard of The Man in the High Castle. That was a famous book by Philip K. Dick about a different outcome in World War II. Stephen Fry had one, Making History. Again, it's related to World War II. There seems to be an obsession with alternative history, people about the outcomes of World War II. So it's a popular fiction theme. But there is a branch of people who would call themselves serious historians, who ask themselves the question, what if history had been different? And we've got there books by Niall Ferguson. There's a book up there, Operation Sea Lion. Again, a lot of middle-aged men with an obsession about World War II, and if the outcome of World War II had been different, what would the world be like around us today? So what they try and do is they say, I'm going to change one consequence, and I'm going to play out the story and see what happens. We can do the same in physics, right? I have my mathematical laws that I've derived, and I can change the constants that I put into those mathematical laws, and I can play them out and ask, what would the consequences be? So I could imagine what-if universes. Hypothetical universes, right? What if gravity was stronger? Now, of course, I mean gravity stronger in relation to the other forces, right? What if the electron was more massive? What if atoms were more or less stable? What if there were different numbers of dimensions of space and time? What would the universe have been like if we tinker with those basic laws at the bottom? And would those universes be able to host life? Now, you might be thinking to yourself, well, okay, if I mess around with the mass of the electron, and then I might get, slightly different atoms. So maybe it all just sort of irons out, and, life in the universe, or even the universe around us, is pretty robust to these changes. But let's think about this for a second, right? What we're talking about is messing with the fundamental building blocks of the universe, the fundamental masses, the fundamental forces. So here, right, we've got an atom, it's a proton and a neutron. So that's a deuterium atom with one electron going around. And I'm going to mess around with the physics and change the properties here. Well, of course, I know that if I start messing around and I start changing individual atoms, well, individual atoms have to join together to give us molecules. So if I change the atoms, does that change the way that they can join together to give us molecules? Now, the molecule that we've got on the slide here, of course, that's DNA. So clearly, if I change atoms so they join up in a different way, not form DNA, then life like us would be problematic. Okay? Of course, those complex molecules, you put them together, they give you cells, and you put cells together, and ultimately you end up with life. What we have, of course, is the question we're asking is if I mess around with the stuff at the bottom, the fundamental bits and pieces, how do those changes propagate themselves up through the scales to the macroscopic universe? Is the large-scale universe robust to those changes, or is it sensitive to those changes? So let's take a look. What we've got here, again, is that deuterium atom. And a deuterium atom, right, is clearly the fundamental forces in action, right? The nucleus is held together by the strong force. So if I start to mess around with the strong force, then maybe protons and neutrons won't stick together. Well, that's already a bad thing, because if you can't get protons and neutrons to stick together, then how do you form heavier elements? If I mess around with Planck's constant, then I change the action of quantum mechanics. Now, it's quantum mechanics that keeps electrons out of the nucleus of an atom. If an electron can get into an atom, then it joins with the proton and they turn into a neutron. So if I mess around with the limits of quantum mechanics, I don't have protons and electrons anymore, I have neutrons. So you can already imagine that if we start to mess around with stuff, the building blocks from which the complexity of the universe is made will disappear. This, of course, is the astronomer's periodic table, right? Here you've got all of the elements that you have in the universe, right? The natural elements, and the sites at which they're formed. So we've got hydrogen and helium, they made in the Big Bang. Then we've got all the other elements, some made in lighter stars, some made in heavier stars, some made in catastrophic explosions. If I mess around with strong force, right, and I prevent protons joining with neutrons, then what I can do is I can simplify the periodic table, right? I can get rid of all those elements. If I just change the binding of protons and neutrons, then I don't form any heavier elements. And the only element that we would have in the universe would be hydrogen. Now, hydrogen, of course, is a very versatile molecule, atom, right? You find it in lots of things, but it needs things to bind to. Now, if you remember your chemistry, if you've got hydrogen, then only hydrogen can form one particular molecule, and that's H2. So if I live in a universe where I had messed around with the strong force such that I couldn't form heavier elements, then this would be chemistry. Okay. Now, of course, chemistry textbooks would be really thin. They'd only be basically a page or two. Chemistry exams would be very simple, because all you would need to do is calculate the chemistry of neutral hydrogen and hydrogen molecules. But notice what we've done, right? We messed around with the strong force. We stopped the ability of heavier elements being formed. So what we ended up doing was robbing the universe of complexity. And what we have now realized is that life like us, well, any life we can imagine, needs complexity, okay? We need to have something more than just one particular molecule for us to build up structures that can process energy and information, do all the things that life is known to do. So in a universe that we have messed around with the strong force that much that we can't form heavier elements, the prospects for life are pretty dismal. The notion, okay, so I can't go through all of the examples here, I'll go through a couple of them, but the notion is something like this picture that we've got here. What we find is that when we look at the fundamental properties of the universe, strength of the strong force, strength of the weak force, gravity, stability of atoms, etc. What we tend to find is that there is a relatively narrow range over which those particular properties result in complexity of the universe. And if you stray too far from that range, then what you find is that complexity is destroyed and your universe is too simple to host the complexity of life. So this is known as the fine-tuning problem, okay? So the fine-tuning problem is essentially, why does our universe appear to have the collection of fundamental properties that allow us to be here? Now, some of you are already saying, and I know a lot of my colleagues do, is that now clearly aren't we in some sort of tautology here, right? If our universe wouldn't have allowed us to be here, then we wouldn't be here asking that particular question. But we can still ask, right? What about the overall properties of the universe allow the complexity that we see around us? So this is the fine-tuning problem. And as I said, there's lots of examples. You can take a look at my book, but there's also plenty of free online resources that discuss the various ranges over which these fundamental properties can vary before you destroy complexity. And some are broadish, some are very, very narrow, some are very fine indeed. Now, again, what we have to remember is that I've spoken about complexity to make us. But the complexity to make us is, as I said, it's the fundamental forces at work. But they have been fundamental forces at work over billions of years. So what we've got here, this is a computational simulation of a universe. So this is known as the Illustrious simulation. It took about 5 years to basically calculate this particular simulation. What you do is you make a synthetic universe on a computer, you put in the laws of physics, so you put in the expansion of the universe, you put in gravitational attraction, you put in how gas moves. Now gas is very complicated because gas has pressure and temperature and density, and gas can collapse and form stars and change phase. But you put all that kind of stuff in and you evolve it. And what you find, of course, is that in the early universe was very simple. It was made of hydrogen and helium. But to make the heavier elements on which we are made, then those lighter elements have to be processed. And they are processed in the hearts of stars. So gas collapses, you get nuclear furnaces igniting in the hearts of stars, you get hydrogen turned into helium, helium turned into beryllium, after carbon, oxygen. You get supernova explosions, that creates heavy elements. So if you've got any gold jewelry, at least I was told it was gold, gold is produced only when massive stars die. So to produce this complexity, then there's a lot of physics that had to bring us to this particular point. So if you mess around with aspects of this line of physics, then you could break that chain. You can end up with a simple universe. And the universe that we can see here, this represents, as I said, the universe that we can see around us. It contains the physics that we understand, and it produces the heavier elements which we are made of. But again, if we mess around with the bits at the bottom, maybe I can change the entire history of the universe. So let's think about that. I could make gravity too weak. So I can make the universe identical. Imagine the universe born in the Big Bang exactly the same way as it was made in our universe. But let's just make gravity too weak. What does that do? Well, I've still made hydrogen and helium, and the universe has got hydrogen and helium buzzing around, but gravity is now so weak is that gas cannot collapse into stars. If you don't form stars, you don't make heavier elements, you don't get complexity, you don't get us. So if gravity goes below a certain strength relative to the other forces, no stars, no complexity, no life. I could go the other way, right? I could increase gravity by a little bit. Now, you might think, oh, well, what's the effect of that going to be? So here's the sun. How does the sun operate? Well, the sun, as I mentioned, like all stars, is a giant nuclear furnace. Gravity squeezes the core and heats it up, and the temperature goes up. That produces nuclear reactions. Those nuclear reactions produce pressure and energy flow, which supports the sun. So the sun is balanced, right, between gravity squeezing inwards and the other pressure and radiation pushing outwards, which is the electromagnetic force. And the sun has been stable for roughly 5 billion years, and many stars are stable over extended periods. Now, that stability is a relatively fine thing. We know that as the sun gets older, right, it becomes more bad-tempered, as we all do as we get older. And the sun will basically not be able to maintain that stability, as we all do around the middle, right? And the sun will eventually end up oscillating. And in the end, its outer layers get puffed off. But if we mess around with gravity and make gravity too strong, then that gravitational squeezing can make the nuclear reactions at the heart of the sun unstable. And instead of burning stably for 5 to 10 billion years, it might only do it for 10 million years or 1 million years. Timescales far too short for planets to form and life to arise. So the stability of stars themselves, right, depends upon exactly where gravity is relative to the electromagnetic forces. And we ended up with a value that's allowed long-lived 10 billion-year-old stars like the sun. Of course, if we wind up gravity too strong, then what happens is that soon after the Big Bang, everything collapses. And gravity is so strong that nuclear reactions don't support stars anymore. Things just collapse into black holes. So instead of the universe just being filled with hydrogen and helium, we have a universe filled with black holes, no elements, no complexity, no life. So gravity has to be in a relatively narrow range for there to be the raw material for stars, for them to collapse together, stable stars, to give you environments in which life can form. Now, I'll mention another feature, and what we're going to talk about here is not, well, we don't really know what this stuff is yet, but we think it's something fundamental to do with the universe. When I was younger, the universe was relatively simple. All we had to worry about was how much matter there was in the universe. So as a cosmologist, I know that the universe was born in a Big Bang roughly 14 billion years ago, and the universe has been expanding, and that rate of expansion depends upon what's in the universe. And if you've got matter in the universe, the rate of expansion is always slowing down, constantly slowing down. And so these are the possible pictures we had for the evolution of the universe, from the Big Bang at the bottom to the top, and each one has a different amount of matter. So the one on the far left has a lot of matter, so gravity pulls it together and it collapses. The one in the middle has just the right amount of matter, so you get nice sedate expansion. The other one has too little matter, you get quite rapid expansion. And this picture, we want to know just how much matter was in the universe. This was really nice up until about the mid-1990s, and then there was a problem. And the problem came from these objects. So this here is a star at the end of its life. It's a massive star. It's burned through all of the various elements. It's gotten to the point where it's now made iron in its core. Iron can't undergo nuclear reactions. Star explodes and gets really, really bright. And you can see it from across the universe. So this, of course, is a supernova. And I'll show you this little picture here. So the supernova in this picture, that's the dot in the bottom left-hand corner. That is a star in that galaxy you can see. So that galaxy has roughly 200 billion stars in it. For a period of around 2 weeks, that individual supernova puts out more energy than those 200 billion stars put together. We can use these supernova to chart the expansion of the universe, right across the universe as far as we can see with our telescopes, and we can measure the expansion, and that tells us what's got to be in the universe. And what we found is that instead of the universe slowing down, the universe is accelerating. So in 1999, we realized that our expansion was accelerating. This means there has to be something more than just matter in the universe. So there's this stuff, astronomers are terrible at naming things, that we call dark energy, which is driving the expansion. Now, what we've realized is that dark energy just isn't a bit player in the universe, but it's the dominant source of energy in the universe. Roughly 75% of the universe's energy is in the form of dark energy. So you'd think that we would know where this dark energy comes from. And people have looked. A lot of people have wondered if dark energy is to do with something known as the quantum vacuum, right? So you've got an empty patch of space, but in quantum mechanics, that patch isn't really empty, but it seethes with energy. Particles pop in and out of existence, right? It's a really weird place. So what you do is you say, right, I understand the quantum vacuum, I do a little bit of maths, and I calculate how much energy I expect there to be in the vacuum based upon quantum field theory. And you do the calculation, and you work out the number, and you compare that to what we observe in the universe. And the answers don't quite agree. In fact, they differ by a factor of around 10 to the 120. Oops, slides getting ahead of themselves. Sorry about that. Differ by a factor of around 10 to the 120. So our theoretical prediction is that there is 10 to the 120 times more energy in the vacuum than we measure when we look at the universe. And we don't understand why. This is the most obvious place where the source of dark energy should come from, but why we have got this minuscule amount compared to what we expect. So there's a huge possibility of potential dark energy densities that would be much better than the value that we see. But if dark energy was anywhere remotely close to this particular value, what kind of universe would we have? Well, if dark energy has particular properties, we would have a universe which is basically born, but in a millionth of a second, collapses again due to the actions of dark energy. Now, I hope you can agree that in a millionth of a second, the prospect of life forming in a universe would be rather minuscule. Or we could go the other way, and we can have dark energy, which is positive, and you create a universe, and it expands, but expands exceedingly rapidly. So you still produce your hydrogen and helium, but then the universe basically empties out. And what you end up with is you end up with basically one solitary proton per observable universe that sits there in the darkness, and then every 100 billion, trillion years, another proton comes along, and off it goes and gets lost back into the void. Again, I hope you agree that prospects for life in a universe where there's one proton per observable universe are negligible. So we have dark energy, and we have a minuscule amount of it compared to the possibilities, and we are lucky that we have that particular value, because if it had been slightly different, we would have ended up with a very, very different kind of universe. So the question is, what does the fine-tuning? Where does the fine-tuning come from? This is where we stray more into the realm of philosophers. If you're in the pub with cosmologists, this is where the arguments start to break out, okay? So, a fine-tuner. What am I talking about as a fine-tuner? Well, we could take the laws of the universe like a game of chess, right? A game of chess has set rules that the pieces must follow, and that's how the game is played out. So who came up with the rules? Who came up with the rules of the universe? So let's take a look at some of the philosophical suggestions. One of the ones that really results in a lot of arguments is that we live in a simulated universe. And what I mean by that is that our universe is like the universes that we generate on our computers. In the sense that, in the same way that I can write down the laws of physics in mathematics and transcribe those into computer code, that somebody in a universe above is running a simulation in which we are part of the outcomes. They wrote the laws of physics, they're running a simulation, and here we are. And of course, that actually raises lots of philosophical questions about the people running the simulations. Have we pushed this fine-tuning question just to them? Do they live in a similarly fine-tuned universe? Or is their universe fundamentally different to ours, such that there's no fine-tuning problem, and their simulations are to explore what would happen in a finely tuned universe. Now, of course, again, how you would tell that this is a simulated universe, that's the realm for philosophers. Other than a big game over sign appearing in the sky, we have to sort of hope that we're not some sort of undergraduate project and somebody's going to be done with this simulation and pull out the plug and that's it. But this is a serious one where a lot of philosophical discussion goes on about whether or not the universe is a simulation. And of course, Elon Musk has been pushing this idea for a while. He says as computers get more powerful, we will simulate universes on computers, and we too might end up generating conscious beings within our simulations. Almost straight into science fiction. I have to mention, of course, there is a group of people that take the apparent fine-tuning of the universe as evidence of a fine-tuner in a theological perspective, right? That there is a God or gods that basically set up the universe and run the universe the way it is for us. But what I want to do is go back to the scientific. What do we do with this information in terms of a scientific question? Now, a lot of people say, well, clearly all we need to do is we need to do more physics, right? One of the things that we've understood is that as we do more physics, the number of fundamental constants seems to decrease. Electricity and magnetism used to be two separate topics, and you would have permittivity and permeability in electricity and magnetism. When Maxwell worked out his equations of electromagnetism, he showed how those two constants could be brought together into one constant, which we now call the speed of light. So maybe if we just keep doing more physics, we'll reduce the number of fundamental constants down to zero. Maybe we will find that Newton's gravitational constant is a combination of pi and E and some other mathematical terms. And maybe we will. Now, it doesn't look like we're going that way, but maybe we will. But it doesn't really answer the fine-tuning question at the end of the day. Because, of course, mathematics, the mathematics of the universe, is a possible set of mathematics. And in mathematics, of course, there are other ways mathematics could work. So the question that we would still have is why this mathematics and this mathematical set to explain the universe around us? And physics then offers no answer. What else do you do? You've got your mathematics. What else do you do? You have to go somewhere else into metaphysics to try and explain why we have the physics that we do. But I'm going to mention the answer that I sort of lean towards. And again, this is a personal preference. I have no proof or evidence in a particular way, but this is the notion that you get around this by having more than one universe. So here we have our universe, but a lot of people have suggested that our universe is not alone. That our universe is one of many other universes in this overall thing known as the multiverse. Now, how many universes are out there? Well, that's a good question, right? We don't really have a theory for multiverses, right? We don't know how you create multiverses. We don't know how multiverses would create individual universes. But people have made some suggestions, and the number of other universes is a number, they say, take this with a grain of salt, something like 10 to the 10 to the 10 to the 7. That there's possibly that many other individual universes that are out there, okay? Now, of course, that number is very, very rubbery. It could be 2 universes, it could just be 1 universe, or there could be an infinite number of universes. But if you apply some physical reasoning, this is the kind of number you get. So potentially a huge number of other universes. And one of the things that they suggest is being guided by string theory, that in each of these universes, right, effectively there's a roll of the dice when the universe is created, right? And that roll of the dice imprints each individual universe with its own laws of physics. Different mass of the electron, different speed of light, different amount of cosmological constant, different number of densities of space, dimensions of space, different dimensions of time. If that's the case, then what we know is that most of these universes would be dead and sterile, right? They wouldn't have complexity in them. They might have 1 proton per observable universe. They might have just a sea of hydrogen and helium. They might have, not enough dimensions for complexity. They might have too many dimensions of time for physics to be predictable. But most of them would be dead and sterile. So why do we find ourselves in a universe that can host complexity? It's because out there's a sea of other universes, and we were lucky in terms of the roll of the dice that when our universe was created, that we got the laws of physics that allowed the complexity for us to be here. So this, for a lot of people, is taken as relatively strong, in inverted commas there, evidence that we live in a multiverse. That this is a natural way that we can solve the apparent fine-tuning problem, is that we are one universe in many, many universes, but most of them are dead. So I think I'm at time. I'll finish there. I'll put up the book again if you want to have a read. It makes for an excellent Christmas present, by the way. And if you want to ask any questions after the talk today, feel free to ping me on Twitter at Cosmic Horizons, and I'll be happy to answer your questions. So thank you.
Fantastic. Thank you very much, Geraint. We do have a bit of time for some questions. First of all, can I just say the simplified chemistry that you put up was getting a lot of love in the chat. There are a lot of people who are very on board with the idea of hydrogen being it. So I think we should just go with that. We got huge numbers of questions that have come through. As usual, I'm not going to get through them all, so my apologies if I don't get to yours. But let's start with this one. It's sort of a philosophical one about your theory or your work as a whole, which is, if you're going to be playing around with these sort of model universes, changing this and that and so on, that's great. But what does that do for us? What does it help us to understand? Can you sort of encapsulate? And I know that's the point of the whole talk in a way, but can you encapsulate for us in a sense? Why do we do this? Why do you play with these model universes to make these models?
Well, can I give you the Mallory answer, right? I mean,
yeah.
Why did Mallory climb Everest? Because it's there, right? No, so for me, the fine-tuning question is a real physics question about the universe. Why this universe? Now, as I said, lots of physicists don't work that way. You can only work with the universe that we have. But there are people working in string theory, working in multiverse theories, all of the theories at the cutting edge. They're trying to see through the Big Bang to ask the question where the universe came from. And we may end up one day with a picture of how you create universes. So the next question will be, well, what kind of universes come out of there? So we effectively are doing the groundwork. We are saying, if it's this kind of universe, it will evolve that way. If it's this kind of universe, it will evolve that way, right? It will provide a measure of the potential of that theory to create universes that we know and universes that we don't know. Okay, so can I give you another example?
Yeah.
So we're in a similar situation now to what the gravitational wave people were in the 1960s, in that they, at some level, didn't know if gravitational waves were detectable, but they still calculated the theoretical signals that would be seen in the gravitational wave experiment, hoping that in the distant future, we will have gravitational wave detectors that will be able to say, look, this is a black hole colliding, this is neutron stars colliding, etc. So we are pushing the theory ahead of the next theoretical and hopefully observational breakthrough about understanding where our universe came from. Is that a satisfying enough answer?
I think so. And the gravitational wave thing, that makes a lot of sense. I can remember as an undergraduate back when there were still dinosaurs roaming at that point. But a seminar from someone who was doing pioneering research on very early gravitational wave stuff, coming around talking about this is how we're going to build a thing. And you know, you could feel the sense in the room of all these physicists going, "You're nuts! We're never going to be able to do this." Here we are, 2021, and we're doing it routinely all the time.
Absolutely.
So next question. A sort of central part of a lot of what you're talking about is around, look, if we change this or we change that, we wouldn't be here. But there's been a fairly strong series of questions saying, yeah, but how do we know that you couldn't get life in some other way? Why are we defining life so carefully around what we are? So could you talk to that a bit?
Yeah, so that's one of the things that we banged our head against the wall a little bit about when we wrote the book, is defining life. And I'll tell you what, there is no point talking to a biologist, because there is no definition of life, right? Because you end up, I mean, we've got coronavirus going around the world at the moment, and we still don't know answer the question, is a virus alive, right? So what we said is that we need to define life in a more general way, and that general fashion is to do with complexity, right? So life, as we understand it, is something that processes information and energy, and you process information and energy with complexity. Now, Schrödinger, if the students listening have ever read Schrödinger's excellent book, What is Life, which he wrote in the 1940s, a physicist's view of life, he pointed out that a crystal cannot be alive because a crystal is just a simple thing that repeats. You need complexity for that information storage for life. Where does complexity come from in our universe? It comes from molecules. And in particular for us, it's the carbon molecule. And carbon, of course, we know has very particular chemical properties, in that if you look at the molecules you can create, you go along the periodic table, it goes you hit carbon, it goes through the roof, comes down again, and then the next one is silicon over here. And silicon's a smaller bump. So for us in this universe, it's really about carbon, right? It's carbon that is the key thing. So if you imagine that I could stop carbon being made in this universe, and there are easy ways to do it, then the backbone of complexity disappears, and it's very hard to imagine that you could get life without that backbone. Now, you could imagine a science fiction-y kind of picture if you want to, and we do talk about some of those, but it's very hard to put some of those science fiction pictures into a physical basis on how they would process information and energy. But of course, there's always going to be that fuzziness about how you define life, but that's the way we did it.
It's one of the things I really like about reading around this topic, and by no means am I an expert, but I've done a little bit of reading in preparation for this, is that every one of these questions you can come up with is, yeah, but what about this? Someone's thought about it and actually done the calculations on it. You've actually written down the equations and go, well, if it was like that, then this would happen. Oh, you've thought of that. Okay. Wanted to touch on one of the first questions that came through when you were talking at the beginning of your lecture about the various particles and the forces. There was a lot of news just a couple of months ago. All the papers in the world just went, physics has turned on its head because we've discovered this new stuff. And it was about I think the G-2 experiment. And the way that was reported by a lot of people was, maybe there's a fifth force. Maybe there's new physics that we don't understand. Where's your understanding on that? What's your sense in 2021 of, are we on the cusp of new physics, or was that all just a flash in the pan? What's going on?
So I'm going to choose my words very carefully because I've been in this game for a while. So I started my undergraduate degree in 1987. And one of my tutors was Michael Green, who was one of the people that invented string theory. And he told us in our tutorials that any second now, physics is about to be revolutionized. And here we are in 2021, and it hasn't quite happened. The problem that we have at the moment is there are two leading theories, quantum mechanics and relativity. They work extremely well to n-decimal places. They are wonderful theories, but we know that they can't be correct because we can't explain dark matter properly, can't explain dark energy, and we think these two theories should be one. So physicists are desperate for anything that points us in the direction of new physics, i.e. something that goes beyond the maths that we currently use. Now the G-2 result that you mentioned, this was to do with the spin of that chubbier version of the electron, the muon. And the problem that we have is that what we're doing is we're comparing a theoretical prediction with an observational value. And there are uncertainties attached to both. The theoretical prediction is a difficult calculation that requires supercomputers, and there's some given it, and some people are saying that actually it's going to give this way more than go the other way. The observational value has some given it as well. And if you take both of those into account, then you might find that the theoretical and the observational results actually agree. If they do, that again is a great success for current theories, but it's depressing because that just means that maths that we have already works. If they stay apart, then that means that there's an ingredient that we don't have in our physics at the moment that we need to add, i.e. that new physics, new force, etc. But at the moment, I've seen many claims of this is anomalous, it's pointed to new physics, oh, it's gone away, happens quite regularly at the moment.
It's such a strange position to be in, where on the one hand you want to celebrate the fact that, gee, we can do this well. You know, look at this amazing experiment and look at this amazing calculation, and they agree, that's fantastic. Against, oh, gee, we really want a discrepancy so that we can find some new stuff in the gap there. Listen, we're going to have to call it, oh, sorry, go ahead, Geraint.
I was just going to say, just to let the students know, you don't get a Nobel Prize for towing the party line. You get a Nobel Prize for coming up with something that doesn't fit and doesn't work.
Well, that's words to live by. If any of us want to find a Nobel Prize, go and look in the gaps. Find something that fits in the gaps. Listen, we are going to have to finish up there because we've got to take a bit of a break before our next session. Could everyone please, back in your homes, your bedrooms, your living rooms, wherever you are, bang your hands together in the usual fashion, put the applause in the chat, whatever you want to do, for Professor Geraint Lewis. And thank you so much, Geraint. It's always a fabulous discussion. It is traditional here at the ISS, of course, to say a big thank you. We get one of the students to do that. And joining us on the screen is Mahika Jan. And apologies if I get your name wrong there. But take it away from Yellow Group, Mahika, to give a thank you.
Good morning, Professor Lewis. I'd just like to extend a huge thank you to all students, staff, and amazing speech. You not only inspired us with your passion, but you gave us a lot of knowledge, and a lot of me and my friends and people are very excited to follow your research and what your theories are. Thank you so much.
Thank you, and I hope to see you all here at the University of Sydney sometime.
That would be great. Thank you so much, Mahika, and very, very sorry for almost forgetting until I saw you pop up on the screen there. So thank you very much for that. Thank you, everyone, and we'll see you at the next session.